In 2025, astronomers reported one of the clearest answers yet to a problem that had been bothering cosmology for decades. Where's the missing ordinary matter of the universe? This was not the dark matter mystery. Dark matter is still unknown, and scientists still do not know what particle or substance makes it. The missing matter in this case was normal matter, also called baryonic matter. Baryons are particles like protons and neutrons, the material needed to build atoms. Stars, planets, gas, dust, oceans, rocks, and human bodies are all made from baryonic matter. Scientists knew this matter existed because the early universe had already left a record of how much should be there. The problem was that when astronomers looked at the modern universe, they could not find enough of it. ESA's Planck mission measured the cosmic microwave background, the ancient afterglow of the Big Bang, and helped refine the universe's composition. According to those results, normal matter makes up only about 4.9% of the universe's total mass-energy content. Dark matter makes up about 26.8%, and dark energy makes up about 68.3%. So normal matter is already a small part of the full universe. But even inside that small part, astronomers had a missing inventory problem. The early universe told scientists how much ordinary matter should exist. Big Bang nucleosynthesis, which explains how the first light elements formed, also supported that number. But when scientists counted matter in stars, galaxies, cold gas, hot gas in clusters, and other visible systems, they came up short. A large fraction of normal matter was not where it was expected to be. This became known as the missing baryon problem. The important detail is that the matter was not missing from the universe. It was missing from our observations. It was too thin, too spread out, and too difficult to detect with older methods. For many years, simulations suggested the answer. They predicted that a large amount of ordinary matter should exist outside galaxies, spread to the cosmic web as diffuse ionized gas. This gas is often connected to the warm-hot intergalactic medium, or WIM. The term sounds simple, but the object is hard to observe. The gas can be very hot by human standards, but extremely thin by cosmic standards. It does not shine brightly like stars. It does not form easy targets like galaxies. It sits between galaxies, stretched across enormous distances, with electrons separated from protons. That is why the missing baryons were so difficult to count. A telescope can easily see stars because stars produce light. It can see galaxies because galaxies contain huge numbers of stars. It can see some hot gas in galaxy clusters because that gas can emit X-rays. But the thin intergalactic gas outside galaxies is much harder. It can affect light passing through it, but it may not glow strongly enough to be seen directly. Scientists used several methods before the fast radio burst breakthrough. Quasar absorption studies look for signs of gas by studying how gas absorbs light from bright distant quasars. X-ray observations search for hot material near clusters and filaments. Sunyaev-Zel'dovich measurements look for interactions between hot electrons and cosmic microwave background photons. These methods provided evidence, but each had limits. Some were sensitive only to certain temperatures. Some worked better near dense regions. Some required large corrections. Then fast radio bursts became a new tool. Fast radio bursts, or FRBs, are short flashes of radio waves from far outside the Milky Way. They last only milliseconds, but they are bright enough to travel across huge cosmic distances. Their exact causes are still being studied, but one leading explanation connects many FRBs to magnetars, which are neutron stars with extremely strong magnetic fields. For the missing matter problem, the origin of the burst is less important than the journey the burst takes. When a fast radio burst travels through space, it passes through plasma. Plasma contains free electrons. These electrons affect radio waves in a measurable way. Lower frequency radio waves arrive slightly later than higher frequency radio waves. This spreading of the signal is called dispersion. The more free electrons a radio pulse passes through, the stronger the dispersion. That makes FRBs useful for weighing invisible matter. They act like signals sent to the hidden gas of the universe. If astronomers know where an FRB came from and how far away its host galaxy is, they can compare the distance with the dispersion. The delay in the radio signal tells them how much ionized matter was in the path. This is why localized FRBs are so important. A detected FRB alone is useful, But a localized FRB is much stronger because scientists can identify its host galaxy and measure its distance. Without localization, the signal tells you that it passed through matter, but the distance remains uncertain. With localization, the FRB becomes a cosmic measuring line. In 2020, a major Nature paper led by J.P. McCourt used localized fast radio bursts to measure the baryon content of the universe. The study showed that FRB dispersion could account for ionized baryons along the line of sight and produce a baryon density consistent with values from the cosmic microwave background and Big Bang nucleosynthesis. This was a major step because it showed that FRBs could independently confirm the amount of ordinary matter expected in the universe. But the 2020 result still left a major question. It helped confirm that the baryons were there, but scientists still wanted to know how they were divided. How much ordinary matter sits inside galaxies? How much is in galaxy halos? How much is truly between galaxies? That is where the newer 2025 work became important. In June 2025, Liam Connor and colleagues published a Nature astronomy study called A Gas-Rich Cosmic Web Revealed by the Partitioning of the Missing Baryons. The study used a larger sample of localized FRB sources to separate the baryons into different cosmic locations. The result was clear. The biggest share of baryonic matter is not inside galaxies. It is in the intergalactic medium. The study found an intergalactic medium baryon fraction of about 0.76, meaning around 76% of the baryonic matter is in the space between galaxies. Reuters reported the same result in simple terms. About 76% of ordinary matter resides in intergalactic space, about 15% is in galaxy halos, and about 9% is inside galaxies, mostly as stars or gas. This answer changes the way the missing matter problem should be explained. The missing matter was not locked inside hidden planets or secret galaxies. It was not all in black holes. It was not confused with dark matter. Most of it appears to be thin ionized gas spread to the cosmic web outside galaxies, in regions that look almost empty from a normal visual point of view. The reason this matter exists outside galaxies is connected to feedback. Galaxies are not closed containers. They gain gas, form stars, lose gas, and recycle material over billions of years. Massive stars explode as supernovae and push gas outward. Supermassive black holes at the centers of galaxies can release huge amounts of energy when they feed on gas. These processes can drive matter out of galaxies and into their surrounding halos, or even farther into intergalactic space. So the missing baryons are not just leftover material from the Big Bang, sitting quietly between galaxies. Some of them were pushed there by violent galaxy evolution. Star formation and black hole activity can heat gas and expel it. Over time, this created a cosmic system where galaxies and intergalactic space exchange matter. Galaxies are not isolated islands. They are connected to a larger gas network. This also explains why the missing matter problem matters for galaxy formation. If most ordinary matter is outside galaxies, then galaxies are not holding on to their full baryon supply. That affects how many stars they form, how fast they grow, why some stop forming stars, and how black holes influence their surroundings. The missing baryon problem is not only an accounting problem, it is also a galaxy evolution problem. The 2025 result also matters for precision cosmology. The distribution of baryons can affect how matter clumps on large scales. It can influence lensing measurements and how scientists interpret structure in the universe.